Ladies and gentlemen, good morning. My name is Lin Zhu, PhD student of Huazhong University of Science and Technology. I am honored to have the chance to report our research work at the 50th International Conference on Parallel Processing. The topic of my paper is Communication Avoiding All Pairs Shortest Paths Algorithm for Sparse Graphs, and this research work was done in cooperation with me, Changsheng Hua and Hai Jin. We introduce our work in 5 parts, followed by background, several algorithmic techniques, our method, proof of lower bound and summary. Well, let's move on the first part of this topic. The research problem of this work is the calculation of the all-pair shortest path of undirected weighted sparse graphs. That is, let G be an undirected weighted graph with a vertex set V, edge set E and weights W. The all-pairs shortest path problem computes the length of the shortest paths between every pair of vertices in the graph. Let's move to the theoretical model of our research. In the distributed memory model, there are P processors. Each processor has a memory of size M words, and the processors communicate with each other via a network model. We count the communication cost in terms of number of words and number of messages. The architecture is homogeneous in this model. And each processor can communicate with one processor at a time. Besides, we assume that there is a link in the network between each pair of processors, that is, the network has all-to-all connectivity. Here, we introduce related work. There are mainly 3 works that are closely related to our research and are also our motivation for studying this problem. The first work is the 2DDC APSP algorithm, which is the communication optimal APSP algorithm under the distributed memory model. The second work is the Super FW algorithm. This algorithm reduces the computational cost and has a smaller work and depth for sparse graphs in the shared memory model. The third work is the D-sparse LU3D algorithm. This algorithm computes the LU factorization of a sparse matrix in the distributed memory model. However, there are few studies focusing on low communication complexity APSP algorithms for sparse graphs in distributed memory model. Here is the research goal of our paper. One is to design a low communication complexity APSP algorithm for sparse graphs, and the other is to give the communication lower bounds. These are the conclusions obtained in our paper, which implies that the bandwidth cost of our algorithm is nearly optimal and the latency cost is optimal. We briefly introduce the classic Floyd-Warshall algorithm. In each iteration, each element in the distance matrix A is updated once. Blocked Floyd-Warshall algorithm divides A into multiple blocks, and at each iteration k, all blocks will be updated. As shown in the figure, when k equals 3, the red, green and yellow blocks are updated sequentially. For dense graphs, the update of these blocks is necessary, but for sparse graphs, some can be avoided. At this time, the Floyd-Warshall algorithm may not be so efficient. How to avoid the update of certain blocks for sparse graphs? We need to use some algorithmic techniques. In this part, we introduce some algorithmic techniques that are helpful to avoid calculations. When an element of the distance matrix or all elements in a block are infinite, then the corresponding calculation can be avoided. For example, if the element A, 4, 3, is infinite, then in the third iteration, the elements in the fourth row remain unchanged and needn't to be updated. It is similar for block A, 4, 3. However, even if the adjacency matrix A is sparse, the sparse structure of A is irregular and there may not be all infinite values in a block. Here, we introduce nested dissection ordering or ND process for short, which can reorder the adjacency matrix such that the infinite values are arranged in one block. The ND process recursively find the vertex separator S that partitions V into 3 disjoint sets, V1, S and V2. The union of V1, V2 and S is V, and meets 3 conditions. First, there are no edges between V1 and V2. Second, V1 and V2 are roughly equal. Finally, S is as small as possible. V1, V2, and S are called supernodes. The vertices within V1 and V2 have consecutive indices, and vertices in S have a higher index. As shown in the figure, the separator of the input graph is 3, then 3 is relabeled as 7, and the 3 vertices 1, 2, and 7 on the left are relabeled as 1, 3, 2, and the 3 vertices 4, 5, 6 on the right was relabeled as 4, 6, 5. It can be found that after reorder, all entries in blocks A, 1, 2, and A, 2, 1, are infinite values after the ND process, we get 3 supernodes V1, V2 and V3. When the 3 supernodes are eliminated in the order of 1, 2, 3, or 2, 1, 3, the elimination of 1 and 2 are independent, and the elimination of supernode 3 depends on 1, 2. This dependency is represented by a tree called elimination tree. This dependency is represented by a tree called elimination tree, or E-tree for short. As shown in the figure, by recursively calculating the separators of V1 and V2, a 3-level E-tree can be obtained. Because the ND process and E-tree can avoid the update of some blocks, it can reduce the computational cost. However, our goal is to reduce communication cost. How to minimize communication under distributed memory model is still an unsolved problem. In this part, we introduce how we reduce the communication cost in the distributed memory model. First, we map it to the processor grid in a block layout. We use A, K, D, K, and C, K to represent the set of all ancestors, descendants and cousins of supernode K respectively. As shown in the E-tree, the ancestor nodes of 9 are 13, 15, the descendant nodes of 9 are 1, 2, and the other supernodes are cousins of 9. We use QL to represent the collection of the L-level supernodes, and RL to represent the updated region of A during the elimination of the L-level supernodes. If I or J is a cousin of K, then the elimination of K will not update the block A, I, J. Based on this, we can get the updated region RL of A during the elimination of the L-level supernodes. As shown in the figure, the black region is the update area of A during the elimination of the second-level supernodes. We divide RL into 4 subsets, RL1, RL2, RL3 and RL4, and introduce how to communicate between processors to update each subset. Among them, RL1 is the set of all blocks AKK, RL2 is the set of all blocks whose row or column is K, and the other is the ancestor or descendant of K. RL3 is the set of all blocks whose rows and columns are a descendant of K, and RL4 is the set of all blocks whose rows and columns are both an ancestor of K, as shown in the figure. R21, R22, R23 and R24 are the red, yellow, green and blue areas respectively. For each block A, I, J, in RL, its update is shown in this equation. Next we will introduce how to communicate between processors to update those 4 subsets. According to this equation, since for all blocks in RL1, RL2 and RL3, the row and column cannot both be the ancestor of K, so each matrix block can only be updated by the elimination of one supernode. This means that the matrix blocks in RL1, RL2 and RL3 can be updated in parallel and only need to be updated once. The update of these matrix blocks can be done through the broadcast operation of the processor row or column. As shown in the figure, for the update of R22, the red processor broadcasts to the yellow processor along its rows and columns. For the update of R23, the yellow processor broadcasts to the green processor along its rows and columns. Here we introduce the update of all blocks A, I, J, in RL4. According to the update equation, A, I, J, will be updated by the elimination of at least 2 supernodes. Suppose that there are Q supernodes eliminated to update A, I, J. A trivial communication strategy is that each processor send local data to P, I, J, in sequential, then the latency cost is at least Q. An optimized strategy is that each processor send local data to Q different processors. Each processor performs calculations and reduces to P, I, J. The latency cost is log Q. It should be noted that there are more than one block A, I, J, in RL4 needs to be updated. In order to allow all blocks in RL4 to be updated in parallel, we hope to allocate each computing unit that update RL4 to a separate processor, so that all computing units can be calculated at the same time, and the results will be sent to the corresponding processors through the reduction operation. To allocate each computing unit to a separate processor, it needs to meet the condition that the number of computing units is less than P. We can get this conclusion by summing the number of units of each A, I, J. Here we get a mapping from computing units to processors, and prove that this mapping is 1-to-1. Based on this mapping and the previous analysis, we design the communication strategy between processors during the elimination of LTH-level supernodes, and thus propose our algorithm. In this part, we introduce how to prove the communication lower bound of distributively computing a PSP for sparse graphs. The computation of matrix multiplication and a PSP can both be expressed in a 3-nested loop way or 3NL for short. Informally, the 3NL computation model meets two conditions. First, there are two non-trivial parameter-dependent functions Fij, Gij such that C, I, J can be calculated by performing functional operations on A, I, K, and B, K, J. Second, the mapping from elements in A, B, and C to memory locations is 1-to-1. Gray-Ballard et al. Gave the communication lower bound of the 3NL computation model in the distributed memory model, which is related to the number of operations F and memory size M. In order to get the lower bound of communication, we first prove that computing the APSP of a sparse graph is a 3NL computation. And then, we prove the lower bound of operations by calculating the number of operations required in the elimination of the top-level supernodes, which is a part of the total operations. Finally, by applying the lower bound of the computation operations and M to the communication lower bound of 3NL model, the lower bound of bandwidth and the trivial lower bound of latency can be obtained. Besides, by summing the lower bound of the latency cost during the elimination of each level of supernodes, another lower bound of latency cost can be obtained. In this part, we summarize the main contributions of this paper and compare them with previous work. Due to the lack of research work on sparse graphs in the distributed memory model, we compare with the dense graph algorithm 2DDC-APSP. It can be found that the bandwidth cost and latency cost of our algorithm are asymptotically lower than the 2DDC-APSP algorithm. And the bandwidth cost of our algorithm is nearly optimal and the latency cost is optimal. Okay, ladies and gentlemen, it has been my pleasure to give you my viewpoints on communication avoiding all pairs shortest paths algorithm for sparse graphs. Thank you very much for your kind attention.